In this video, we're going to be talking more exclusively about bending moments, okay? Now, in the previous video, we talked very briefly about torque moments, but for the purposes of this statics course, we're going to be talking in much more detail about bending moments. So again, a bending moment, again, is a tendency of rotation, okay? Bending moments are tendencies of rotation. Now here's something that's a little different than a torque moment. It's a tendency of rotation like a torque moment, but it's not of a member cross section. It's a tendency of rotation of a member's length. Okay? Now some people say it's a tendency of a member length to want to bend, all right? So that's what we're looking at, and we typically call these M. So torque moments, we usually use capital T. Bending moments, we usually use capital M, okay? And when we use a capital M, it's still a force times a perpendicular distance. But the question is, what is that perpendicular distance? Well, with torque moments in the previous video, that perpendicular distance was often a distance within the member's cross section, okay? Usually to the center of the cross section. For bending moments, on the other hand, the perpendicular distance is usually some kind of length along the member, okay? So let's jump right into some examples, okay? So we'll start with one example here. I want us to compute the bending moment about point O in this figure. So here we have what's called a cantilever beam. I'm going to put that in parentheses here. Cantilever beam. Okay. And we're going to have this force applied at the end of the cantilever beam of 100 newtons. And the length of the beam, this is a side view. You're like looking at the side of this beam. The length of this beam is 2 meters. I'm going to make this fixed point on the left, point O. So we are asked to compute the bending moment about point O. So here's what we do. We say M equals force times perpendicular distance, and we're going to say specifically the moment about point O. So I'm going to use this little subscript here, O, right here. Now, I've mentioned this before, I think in the first video. When you take a bending moment, you are taking the bending moment about a point. So this is a tendency of rotation of your system to want to rotate around or about a point. So if you look at this system, what's happening here is you have this force here, right, 100 newtons, that is trying to rotate this member around point O right here, okay? So again, one more time, you have this force 100 newtons that's trying to make this member, this cantilever beam, want to rotate about point O, all right? So that's physically what's trying to happen. So we're going to say the moment about point O is 100 newtons times 2 meters. Now, here's where you got to incorporate that sign convention, okay? We typically call things rotating counterclockwise positive. So if we call counterclockwise rotations positive, what sign should we incorporate into this little equation for this problem? Well, that would be a negative sign, right? Because again, if you look at this 100 newtons, it's trying to rotate this whole system in a clockwise rotation, okay? So that would be negative. So here we're going to have negative 200 Newton meters. And it's newtons times meters, but I typically put a little dash here. I know it's not newtons minus meters, it's newtons times meters. So sometimes when I write my units, it looks like a little dash, but it's multiply, okay? Now, again, we said this adheres to the right hand rule. So what you can do is you can put your right hand up to the screen and curl your fingers into the palm of your hand. Now, when you do this, you need to orient your hand where your fingers are curling in the direction that the 100 newtons is trying to make. So when you do that, your thumb should be pointing into the screen or into your paper, right? And if your thumb is pointing into the screen or into the paper, that's going to indicate negative. All right, so that's one way of thinking about it with a right hand rule. Some people try to avoid the right hand rule, but I insist that y'all read section 4.1, which discusses the mechanics of the right hand rule. Okay, let's jump into another example now. All right, let's jump into another example. So again, I want us to compute the moment, and we're going to say about point A in this case. And again, this is a bending moment. We're computing the bending moment about point A. So here's point A here. And we have this member that's kind of popping up here. Makes a 60-degree angle with a vertical. And we have 40 pounds here, and we have some dimension lines. We have a horizontal dimension line, 4 feet, and then we have a diagonal dimension line here of 2 feet, okay? So again, we want the moment about point A. So we're looking for this tendency of rotation about point A. Notice that you're gonna have a clockwise tendency of rotation here, all right? 40 pounds is trying to make this whole system rotate clockwise. So we're going to end up with a negative sign somewhere. So keep that in mind. So we have moment about A. We call things going counterclockwise positive. And when we look at this, again, it's force times perpendicular distance, right? So we're going to have a 40 pounds. I'm going to put a negative out in front because it's rotating clockwise, times a perpendicular distance of some sort. So the question is, what's that perpendicular distance? Is it the 4 feet? Not really. Is it 2 feet? No, not really. That perpendicular distance is this total horizontal length right here, which is what? It's 4 feet plus, is it 4 feet plus 2 feet? No, it's 4 feet plus 2 feet times the sine of 60 degrees. How do I know that? Well, you need to get the horizontal component of this length right here. And notice we have this little right triangle. We have an angle coming off of the vertical. So you need to say this hypotenuse length, 2 feet, times the sine of this interior angle to get you this horizontal component, all right? So we're gonna say 40 feet times 4 feet plus 2 times sine of 60 degrees, okay? And when we punch that through, let me get my calculator out and make sure we're getting the same answer. 4 plus 2 times sine of 60 times 40. So I get 229.3 pound-feet with a negative in front, because again, that negative is indicating that it's causing a tendency of rotation to be clockwise. Okay, now here's where you got to be very careful. Okay, this negative, it does not mean the 40 pounds is pointing down. We are not putting a negative here because 40 is pointing down. We're putting a negative here because the 40 pounds is causing a clockwise rotation. So our sign convention is based on rotational directionality, not up, down, left, right. All right, so make sure we understand that. So another way we can write this is actually 229.3 pound-feet, and we can put a clockwise rotation symbol here and not put the negative sign. So you can either put a negative sign here, which means clockwise, or you can omit the negative but put a little clockwise rotation symbol off to the right. Either one is okay with me. You cannot put both of them, okay? If you put both of them like this is wrong, all right? Because then you're saying negative 229 also going clockwise, which is like saying a negative times a negative is a positive, right? So you can't put both of them. You just put one or the other. All right, so let's do another example, all right? Let's do another example. So again, we want to compute the bending moment about point A here, and we're going to have this kind of odd-looking cantilever system, okay? And it has a horizontal length of 3 feet, and then we have a diagonal length of 1 foot, and I've got 60 pounds here, and the angle that member is making is a 45-degree angle, all right? And point A is over here. So I want the bending moment about point A. Again, it's force times perpendicular distance. So what's the force? The force is 60 pounds. That part's easy. What's the perpendicular distance? Again, you want this perpendicular distance. Remember, when we say perpendicular distance, we're looking at the distance that is measured at a right angle with respect to the line of action of the force, okay? So we're looking at a vertical distance right here, okay? Because this vertical distance is measured at a right angle with respect to that 60-pound force. So what is this vertical distance? Is it 1 foot? No. The 1 foot is a diagonal distance. Is it 3 feet? No, absolutely not. All right, so what we're looking at is this distance right here. And what is that distance going to be? Well, that sure enough should just be 1 foot times the sine of that 45-degree angle. Again, this little shape, it makes a little right triangle, okay? So you're looking for that vertical component. So so this perpendicular distance should just be 0.707 feet, all right? So then we can say the moment about point A taking counterclockwise positive is 60 pounds times 0.707 feet. And when we punch that through, we should get 42.4 pound-feet. Now, the question is, do we write this as positive or negative? Well, let's look at this. So this 60 pounds is causing this whole system to want to rotate counterclockwise. Look at that. The 60 pounds is trying to rotate this thing counterclockwise. So again, you can apply the right hand rule. Point your fingers in the direction of the 60 pounds. Curl them into the palm of your hand. Your thumb should be pointing out of the page or out of the screen. And when your thumb points out of the page or out of the screen, that's considered a positive rotation. Again, if you have read section 4.1 about the right hand rule, you should be familiar with that. So we're going to keep a positive here, and we can also put a little rotation of counterclockwise next to this to indicate that that's positive.